The next unit in our class was integration techniques. And the first integration technique, or the first lesson in this unit, was to review basic integration techniques, which really should only involve Calculus 1 stuff. And the most sophisticated tool you have from Calculus 1 is the U substitution. And so this works, this rule, technically speaking, kind of undoes the chain rule. And if you let u equal 1 plus e to the x, notice here that du is equal to e to the x dx. So that can simplify this integral into 1 over u to the third du. And it's now reduced to something that you have a rule for. You can just express that as u to the negative third, and then use the reverse power rule. So that will be u to the negative 2 over negative 2 plus c, which when we resubstitute u in again, gives us negative 1 over 2, 1 plus e to the x, the quantity squared, plus c. And in general, you should always try and see if that works first. It's the simplest, best integration technique. It is the case that parts can work sometimes when this also works, but it's often much more tedious. And U substitutions involve sort of noticing when the du sort of shows up there. So here, what you could try, it's not obvious it's going to work, but if you let u equal root x, which is x to the 1/2, notice what happens. Du is 1/2 x to the negative 1/2 dx, or du is 1 over 2 root x dx. That's almost what we have. We have a over root x, so twice du would equal 1 over root x dx. So this integral just becomes the integral of 2 sine of u du. So that's negative 2 cosine of u plus c, or negative 2 cosine of root x plus c. And because this substitution often undoes the chain rule, usually lets your u equal the thing that is inside of a power, or inside of a sign, or inside of some function. U substitutions can also be used to handle tricky things like this if you manipulate your u. So just try to let u equal x minus 3. Then du is just equal to dx. And the problem is you have not yet replaced this x in the numerator. But you can use your substitution, solve that for x, u plus 3 is equal to x. And this integral becomes the integral of u plus 3 over root u du. And you can actually do this because you can break this up into u over root u plus 3 over root u, which is u to the 1/2 plus 3u to the negative 1/2. The antiderivative of u to the 1/2 is u to the 3/2 times 2/3. The antiderivative of u to the negative 1/2 is u to the positive 1/2 times 2 plus c. So that will be 2/3 x minus 3 to the 3/2 power plus 6 root x minus 3 plus c. And that's pretty much as tricky as a u substitution is going to get. Integration by parts might have worked there. Some of you had a similar test question on your test and did integration by parts and it did work, but this is probably easier. The next technique we learned was integration by parts. So recall that that formula said that the integral of, I have to think of it now, so uv minus integral v du. So this would be u dv is equal to uv minus integral v du. So for here, I will choose u to equal x, which means du is just dx, and I'll pick dv to be cosine of 2x dx, which makes v into 1/2 sine of 2x. So there's my work. So this will equal uv, so 1/2 x sine of 2x, and because I have a definite integral, I must evaluate that from 0 to pi over 2 minus v du. So minus 1/2 the integral sine 2x dx from 0 to pi over 2. Now plugging in pi halves, I will have pi over 4 sine pi minus 0. I think that whole first term is going to be 0. Now on the next one, the antiderivative of sine is negative cosine, so we'll have negative 1/2 cosine of 2x evaluated from 0 to pi over 2. So we've got plus 1/4 cosine of pi minus cosine of 0. So that will be 1/4 times negative 2, or negative 1/2. And it's okay if definite integrals are negative, because this definite integral represents a signed area under the curve x cosine 2x between 0 and pi halves. This negative 1/2 just means that overall that curve is more below the x-axis than above it. Now, integration by parts can also be used to handle integrals like this. Now, be very careful not to mix up your differentiation stuff. You don't know the antiderivative of arcsine of 2x. You know its derivative. So your only option is to let u equal arcsine. There's really no other choice there, which just leaves dx to be your dv. So then the antiderivative of 1 dx is just going to be x, so v is equal to x. And the derivative of arcsine of 2x will be 2 over the root 1 minus 4x squared. The 2 in the numerator comes from the chain rule. So this will equal uv, so x arcsine of 2x minus the integral of v du, so minus the integral of 2x over the root 1 minus 4x squared dx. And even though that second integral isn't ridiculously easy, it is one that you can handle using a regular substitution. We've already used the letter u, so let's pick something different like w. W would equal 1 minus 4x squared. dw would be negative 8 dx. 8x dx. So negative 1/8 dw equals x dx. See, we have x dx. So we'll have, take out that 2. So negative 2, negative 1/8, w to the negative 1/2 dw. So that gives us x arcsine 2x plus 1/4. Now the antiderivative of w to the negative 1/2 is w to the positive 1/2 times 2 over 1 plus c. And all we have to do now is input back in what w was. X arcsine of 2x plus 1/2 times the root 1 minus 4x squared, and then plus c. One of the sort of trickier applications of, or clever applications of integration by parts applies to integrals like these. They're some people call them the around the world integrals. So I'm going to choose to let u equal cosine of 3 theta and let dv equal e to the negative theta d theta. You can reverse that choice, it's just that your work is going to involve more fractions, which leaves you room for more error. So v is negative e to the negative theta, and du is negative 3 sine 3 theta, d theta of course. Okay, now this will equal uv minus v du, so negative e to the negative theta cosine of 3 theta minus v du. And because v and du are both negative, this stays a minus. Pull out a 3. Integral e to the negative theta sine 3 theta d theta. And now we're going to do it one more time. So we'll let u equal sine of 3 theta. Du will equal 3 cosine 3 theta d theta. dv, once again, is e to the negative theta d theta, and v is negative e to the negative theta. So my integral is negative e to the negative theta cosine 3 theta minus 3 times, so uv, negative e negative theta sine 3 theta minus v du, so it should be plus in this case because of the negative v. So plus e to the negative theta plus 3 even, plus 3 e to the negative theta cosine 3 theta d theta. So now distributing some stuff out, my original integral, the integral e to the negative theta cosine of 3 theta d theta is equal to negative e to the negative theta cosine of 3 theta plus 3e to the negative theta sine 3 theta minus 9 times the integral e to the negative theta cosine 3 theta d theta. Now if I add this to that one, I get 10 integrals e to the negative theta cosine of 3 theta d theta is negative e to the negative theta cosine 3 theta plus 3 e to the negative theta sine 3 theta, and then divide by 10, and I have the integral e to the negative theta cosine 3 theta d theta equals negative 1/10 e to the negative theta cosine 3 theta plus 3/10 e to the negative theta sine 3 theta, and of course plus c. The next integration technique we had involved using trigonometric identities to manipulate integrals so that you could use a u substitution. So for this one, because I have cosine cubed, I'm thinking that I'll leave off one cosine and save that to be my du. So make this into the integral from 0 to pi halves. Cosine squared x times cosine x times sine squared x dx. And if I were to let u equal sine x, then du would be cosine x. And I gotta change my bounds and all that jazz, so, you know, x equaling 0 would imply that u was equal to 0, and x equaling pi halves, sine of pi halves is 1, so u is 1. But the only problem is, before I do that, I have to change these cosine squareds into sines. And you can do that using the fact that sine squared x plus cosine squared x is equal to 1. So cosine squared is 1 minus sine squared. So we have the integral from 0 to pi over 2, 1 minus sine squared x multiplied by sine squared x cosine x dx. And now make the substitution. I have the integral from 0 to 1, 1 minus u squared times u squared du, or the integral from 0 to 1 u squared minus u to the 4th. So that will be 1/3 u to the 3rd minus 1/5 u to the 5th, evaluated from 0 to 1, which gives us a third minus a 5th, which works out to be 2/15. So many of these integrals involved using these Pythagorean identities. We also used some half-angle, double-angle identities to evaluate integrals, and that you use when the powers in the sine and cosine are even. So this becomes the integral of 1 plus 2 sine of 2x plus sine squared of 2x. And everything's okay except for that little sine squared of 2x guy. And what you have to remember there is these two formulas, that cosine squared x is equal to 1/2 1 plus cosine of 2x, or that sine squared x is 1/2 times 1 minus cosine of 2x. So we will use the second one, and then our integral is the integral of 1 plus 2 sine 2x plus 1/2 times the quantity 1 minus cosine of 4x. And combine like terms before we integrate. We'll have 1 plus 1/2 is 3 over 2. So 3 over 2 plus 2 sine of 2x minus 1/2 cosine of 4x. So that will be 3 over 2x. The antiderivative of sine of 2x will be 1/2 cosine, will be negative. So 2 negative 1/2 cosine 2x. And then minus 1/2 sine of 4x times 1/4 plus c. So simplifying slightly, 3/2 x minus cosine of 2x plus, minus 1/8 sine of 4x. And we also used Pythagorean identities with secant squareds and tangent squareds and cosecant squareds and cotangent squareds. So here, I guess it might be possible to do it both ways. You probably can. I think that it's easiest, in my opinion, to try to let u equal tangent. And if you're going to do that, if that's your plan, your du is going to be secant squared x dx. You have to save two of those and then change the other two. So that's tangent cubed x, secant squared x dx. So because of the even power on that secant, I can change that secant into tangent. So recall that we have tangent squared x plus 1 equals secant squared x. So this can become the integral of tangent cubed x multiplied by tangent squared x plus 1 secant squared x dx. And I'll make your substitution, and we'll have the integral of u to the third times u squared plus 1 du. It's the integral of u to the fifth plus u cubed du. So we'll have 1/6 u to the sixth. My u is tangent, so 1/6 tan to the sixth plus 1/4 tan to the fourth x plus c. Now it would have, theoretically speaking, also been possible to take this integral and let u equal secant of x. Then du is secant x tan x dx. So you'd have taken your integral and you would have expressed it as tangent squared x secant cubed x secant x tan x dx. And you could have replaced that tangent squared by secant squared x minus 1. So if that was the first thing that came to your mind, that's actually also correct. Your answer will be, 1/6 secant to the sixth x minus 1/4 secant to the fourth x. So actually in that case, either method will work. let's make this integral a little bit less painful by just making it into the root of 4 minus x squared dx. So with a trigonometric substitution of this form, you're going to have to let x equal 2 sine of theta, in which case dx will equal 2 cosine of theta, d theta. So subbing that in, we have the integral of the root of 4 minus 4 sine squared theta multiplied by 2 cosine of theta d theta. And now when you factor that 4 out from the root sign, it gets rooted, becomes a 2, multiplies by this 2 makes a 4, and then you're left with 1 minus sine squared, which is actually, so 1 minus sine squared theta. And 1 minus sine squared is cosine squared, which roots to cosine. So we have 4 times the integral cosine squared theta d theta. So that will be 4 over 2, 1 plus cosine 2 theta, using those formulas that we just reviewed. So that's twice theta plus 1/2 sine of 2 theta plus c. And now we have to change our thetas back into x's, and one problem is this sine of 2 theta. Now there's another trig identity that says that sine of 2x is equal to 2 sine x cosine x. I gave that to you on your test that you took over this unit, and you have to use that to change this sine of 2 theta into regular thetas, not twice thetas. So we'll have 2 times theta. Now inputting the 2 sine x cosine x cancels out the 1/2, giving us just sine x, or sine theta, excuse me, plus cosine theta. And now, so first of all, let's just solve for theta. So x over 2 is equal to sine of theta. Let's use a right triangle. So if this is my angle theta, sine is the opposite over hypotenuse, making this side root of 4 minus x squared by the Pythagorean theorem. So theta itself will be arcsine x over 2, and sine of theta will be the root of 4 minus x squared over 2. Oops, that's wrong. Sine isn't that. Sine is x over 2. Sine theta is x over 2. Multiplied, the cosine now is adjacent of hypotenuse, so that's the root of 4 minus x squared over 2 plus c. And that's the antiderivative of the root of 4 minus x squared. Of course, you can distribute the 2, multiply the denominators, etc., but effectively, that's it. Now, what if you had x squared plus a number? Well, in this case, you're going to have to let x equal to tangent of theta. That's because the Pythagorean identity you're going to use is tangent squared plus 1 equals secant squared. And if x is 2 tan theta, dx will equal 2 secant squared theta d theta. So this becomes the integral, hold on, 2 tan theta multiplied by 2 secant squared theta d theta over, now I'm going to make that the root all to the 5th, and that will be 4 tan squared theta plus 4. So all in all, to pull that 4 out, integral tan theta secant squared theta d theta. Now in my denominator, I can factor out that 4, which becomes a 2 once it's rooted. Then it's raised to the 5th power. So 2 to the 5th power is going to be 32. So 4 over 32. And in my denominator, I will have secant to the 5th of theta. So that becomes 1/8 the integral tangent theta over secant cubed theta d theta. Now, I don't see any obvious way to do a u substitution here, so I'm going to change the tangents and secants back into sines and cosines. So that's 1/8 the integral, tangent is sine theta over cosine theta, multiplied by 1 over, actually that's not right, divided by, so this sine theta over cosine theta is over 1 over cosine cubed theta, which reciprocates, and we'll have 1/8 the integral sine theta over cosine theta multiplied by cosine squared cubed theta over 1, which gives us 1/8 the integral cosine squared theta sine theta d theta. Okay, now solving the integral 1/8 cosine squared theta sine theta d theta, we're going to do a substitution, so we'll let u equal cosine of theta. du is negative sine theta d theta. So this becomes negative 1/8 the integral of u squared du, which is negative 1/8 cosine cubed theta over 3 plus c. And then going back to original substitution, we had that x over 2, well, x was equal to 2 tangent, so x over 2 is tangent of theta. So if this is theta, opposite adjacent, the hypotenuse is the root of x squared plus 4. So I will have negative 1 over, well, 8 times 3, so what's that, 24? And cosine of theta cubed. So cosine will be 2 over the root x squared plus 4, that quantity cubed, which will make negative 8 over 24 times x squared plus 4 to the 3/2 power, which reduces to negative 1 over 3 x squared plus 4 to the 3/2 power. These trig substitution ones are pretty tricky. I mean, you can get, it's really hard to make it work out, so you get a nice integral in the end. Oh, and of course, don't forget your plus c, sorry. Plus c, plus c. Now the next technique we had is partial fractions. And one important thing to understand is the decompositions, and I'd like to ask you what to decompose something into without asking you to find the constants. So if I have x plus 2 cubed as a denominator, this had to have come from some number a over x plus 2 plus some number b over x plus 2 squared plus some number c over x plus 2 to the third. So if that had been x plus 2 to the fourth, you would have had 4 things added up. And because the denominators are linear factors, the numerators are just constants. Now here, I would have had a over x and b over x squared because of the repeated x factor. Then I have a repeated x squared plus 1 factor, which is an irreducible quadratic. So for that, I need cx plus d, the top must be linear, and I need one more because it was squared, the ex plus f, we'll say, over x squared plus 1 squared. Do not solve for the constants. You're not going to get extra credit if you do it. I didn't imply that. It's just list out what they would be. Because these are so tedious, we're only going to do one of them. So first, let's factor the denominator. So that's x times x squared plus x minus 2, which is x times x plus 2, x minus 1. So what we have is that 1 over x cubed plus x squared minus 2x must have come from some a over x plus b over x plus 2 plus c over x minus 1. Or multiplying both sides by this, we get that 1 has to equal a times x plus 2, x minus 1, plus b times x minus 1, plus c times x times x plus 2, which gives us 1 must equal a times x squared plus x minus 2, plus b times x squared minus x, plus c times x squared plus 2x. Or 1 must equal, gathering all the like terms, x squared times a plus b plus c, plus x times a minus b plus 2c, and then minus 2a. And because this side only has 1, you know that minus 2a, the constant, has to equal 1, giving you a equals negative 1/2. You also know that a plus b plus c has to equal 0, because there's no x squared term on the left side. And a minus b plus 2c has to equal 0. Now if I add these two equations together, the b's will cancel, giving us 2a plus 3c equals 0. And inputting the a that I have, I would get negative 1 plus 3c equals 0, which will imply that c is equal to 1/3. And then plugging that into the first formula, we'll have negative 1/2 plus 1/3 plus b has to equal 0. And therefore b will equal 1/6. Plugging in these constants, we have that the integral of 1 over x cubed plus x squared minus 2x dx is the same as the integral of, so a was negative 1/2 over x, b was 1/6 plus 1/6 over x plus 2, and c was 1/3, so plus 1/3 over x minus 1. So that will give us negative 1/2 ln absolute value of x plus 1/6 ln absolute value x plus 2 plus 1/3 ln absolute value x minus 1 plus c. So most of the work there is in finding the constants. This really is just nasty algebra. The integration stuff is not often all that tricky. The next topic we discussed was L'Hopital's rule, and just be aware that L'Hopital's rule is only true if your limit is in the proper form, and that proper form has to be 0 over 0 or some kind of infinity over infinity. And if your limit isn't in that form, you have to make it into that form, or just do direct substitution. So here, if we plug 0 into the numerator, we get 0. If we plug 0 in the denominator, we get 1. And actually, 0 over 1 is totally fine. That's just equal to 0. So that limit is 0 by direct substitution. Don't apply L'Hopital's rule because it's going to give you something that's incorrect. Alright, here we have sine of 5x, arctan of 3x. So sine of 0 is 0, arctan of 0 is 0. This limit is of the form 0 over 0. So apply L'Hopital's rule. The derivative of sine of 5x will be 5 cosine 5x. The derivative of arctan 3x will be 1 over 1 plus 3x squared, so 9x squared, times 3. And we no longer have 0 over 0, so now we just input 0. Cosine of 0 is 1, so my numerator is 5. My denominator is 3 over 1, so this limit is 5/3. Sine x over e to the x over 2. Well, inputting 0 in the numerator gives us 0. E to the 0 is 1, so this limit is actually 0 over 1, which is 0. So once again, direct substitution worked. Alright, here we have e to the x plus x to the power of 2 over x. So this is a different indeterminate form. It's the form 1 to the infinity. And we're not really sure what that is. Now we can't apply L'Hopital's rule right now as is, but we can manipulate this so that we can apply L'Hopital's rule. So I'm going to start by letting y equal e to the x plus x to the power of 2 over x. And then I'm going to natural log both sides. That allows me to pull the power down, and I have ln of y is equal to 2 ln e to the x plus x over x. And I'm going to find the limit of this expression instead. So we'll find the limit as x goes to 0 plus of 2 ln e to the x plus x over x. Now obviously the denominator goes to 0, and the numerator does as well, because when you input 0, e to the 0 is 1, plus 0 is still 1, and ln of 1 is 0. So to this expression we can apply L'Hopital's rule. Now the derivative of the denominator, just 1, the numerator will be 2, 1 over e to the x plus x, because of the chain rule multiplied by e to the x plus 1. That will be over 1. So we have the limit as x goes to 0 plus 2 times e to the x plus 1 over e to the x plus x. And now when I input 0, in the numerator I get 4, in the denominator I get 1. So this limit's equal to 4. Now you're not quite done. This told you that the limit as x went to 0 plus of ln of y was equal to 4. So to find tells you that ln of the limit as x goes to 0 plus of y is equal to 4, moving the limit inside the log function, and therefore the limit as x goes to 0 plus of y is e to the 4th. That's pretty much almost as tricky as L'Hopital's rule will get, but the point is you have to manipulate the thing you're limiting so that you have a form 0 over 0 or infinity over infinity before you apply L'Hopital's rule. And the last topic of this unit was improper integration. So this occurs when one or both of your bounds is infinite, or when the interval, the function you're integrating, has a discontinuity somewhere in the interval. So here, first you must change that upper bound to a finite number, so we'll accommodate this by taking a limit. As some variable, say b goes to infinity, the integral from 2 to b dx over 9 plus x squared. So you have to remember the antiderivative of 9 plus x squared. It's arctan 1/3 arctan x over 3, evaluated from 2 to b. So that's the limit as b goes to infinity. 1/3 arctan b over 3 minus 1/3 arctan of 2/3, which is just some weird number. And you have to remember what happens to arctan as b goes to infinity. The arctan function is bounded by pi halves and negative pi halves. Taking arctan over 3 it's just going to get there more slowly. So this limit will equal 1/3 times pi halves minus 1/3 arctan 2/3. So this integral converges, and it converges to pi 6 minus 1/3 arctan 2/3. Alright, next we have the integral from 2 to infinity, 1 over x times ln of x squared. So first we have the limit as b goes to infinity, 2 to b, 1 over x ln of x squared dx. Just on the sides, we're not going to have to work out changing bounds. Let's integrate 1 over x ln of x squared dx. You will do a u sub and let u equal ln x. In that case, du is 1 over x dx. So this will equal the integral 1 over u squared du, or the integral of u to the negative 2, which will be negative 1 over u, or negative 1 over ln of x. So let's use that here. So that gives us the limit as b goes to infinity, negative 1 over ln x evaluated from 2 to b. Limit b goes to infinity, negative 1 over ln of b plus 1 over ln of 2. Now, because ln is an increasing function, negative 1 over ln of b will go to 0, so this integral converges to 1 over ln of 2. And this final one is the one that most of you missed. So in this particular example, 0 is a problem point because you cannot technically do 1 divided by 0. So what you have to do here is take a limit as b goes at 0 from the right. And that's because you can't root negative numbers. So if you're going at 0 from the left, it means you have sort of numbers that are negative and small. So b to 4, x to the negative 1/2 dx. So that's the limit. B goes to 0 plus. That will be x to the positive 1/2 times 2, evaluated from 4 to b. So the limit as b goes to 0 plus 2 root 4 minus 2 root b. And so 2 root b goes to 0, so this one converges to 4.